Hi everyone, welcome to our second lecture of the second semester. This lecture is a combined lecture for both the Calc and non-Calc students. Okay, today we're going to be talking about the elasticity of materials. So if you remember last lecture when we did statics, we made an assumption about materials that we were working with, and we assumed that they were rigid. And what rigid meant is exactly what it sounds like, is that the object does not deform in any way whatsoever when you apply forces or torques to it, whether it's moving or not. Okay, so when you had the lever, for instance, and you had this bar being held up by the fulcrum, the bar remained rigid. It didn't kind of droop down at the ends as you might expect if the material were more elastic. Okay, so that assumption made life very easy for working with statics, but that's not the way all materials are. Most materials have some elasticity. Well, actually, I should probably say all materials have elasticity. It's whether or not the elasticity is noticeable or not. Okay, so you might say something like steel. Is steel elastic? Well, if you're only applying a few newtons of force, you might as well say that a steel bar is just rigid because it's not going to deform under a few newtons. But if you start to apply a few million newtons of force to a steel bar, it will bend. Okay, and so depending on the range of forces and torques that you're applying to something, you may get away with saying it's rigid, and you may not. Okay, now let me make it more applicable to say people who are in ESS or in PT, say the human body, a bone, like the forearm here. Okay, so the forearm, the bone feels pretty darn rigid. Okay, but that bones do have a little bit of elasticity to them, and when you apply some pressure, they will stretch a little bit, and normally, not abnormally, they will stretch a little bit, and then they'll restore. Okay, human tissue, like skin, obviously has some elasticity associated with it. All materials do. Something like Jello has elasticity. If you have like a block of Jello and you apply force to it, the Jello will deform in a certain direction, and then when you remove the force, it'll spring back. Okay, so that's what we're going to be studying. That's what the elasticity of materials is all about. Now, it's a very complex subject, and it actually goes beyond physics into what's called material science. And so we're actually only going to look at a particular range of elasticity. And that range of elasticity is when you apply a force, and then when you remove the force, the object restores to its original shape. That's not always true. So let's take Jello as an example. If you have a block of Jello and you apply a little bit of force to it, say you're squishing the Jello. Okay, so you got a block of Jello and you apply force, it'll bulge out at the ends, and you apply the force, and then when you let go, it'll restore itself to its original form. But you can imagine what happens as you start to apply even more pressure. As you apply more pressure, what will happen is the material will start to break up inside. It'll start to lose its internal integrity. Little cracks will start to form in the Jello. And then when you let go, it will, spring back, but not to the same original length. Okay, so you've damaged the material. And if you squish even harder, well, then you'll just break it apart completely. Okay, so we're not going to look at forces and torques on an object beyond that which it can sustain, such that it restores itself back to its original form. In other words, we're not going to look in situations where you start to break its internal integrity. Okay, we're just going to look at what's called the elastic limit, and anything within the elastic limit, in other words, forces which are less than some maximum force, those forces will not damage the material, and it'll restore itself back. Okay, now we've actually looked at that last semester, although you may not have thought about it in those terms. That's what a spring is. Okay, so if you take a look here at a spring, uh, you have a spring, and if you don't apply any force to it whatsoever, it's going to sit at that dashed line there, which is equilibrium. Okay, now what happens to a spring as I apply force? Well, as I apply force, it'll stretch. The more force I apply, the more it'll stretch. The more force I apply, yet more. Okay, and within the elastic limit, if you then take that force away, it'll restore itself back to equilibrium. Okay, so even in the lab, if you took a spring and you went beyond the elastic limit, you start to damage the spring, and then when you let go, it won't quite restore itself to equilibrium. Okay, so again, we're going to stay within that elastic limit. All right, and we had a formula for that. Now, last semester, just to be clear, I used X instead of delta L. In for today, for this lecture, we're going to use delta L for how much it's stretched. Okay, so F is how much force you're applying to stretch the spring, and delta L is how far will the string stretch. Okay, the formula is basically Hooke's law. Here it is. F is equal to K delta L. Now, last semester I had a minus there because we were worried about directions. I dropped the minus sign and just because I'm not particularly worried about the direction here. It's only magnitudes, okay? So if you have a certain amount of force F, you'll get a certain amount of stretch, okay? More force, more stretch. And they are linearly related. In other words, you double the force, you're going to double the stretch. You triple the force, you're going to triple the stretch, and so on, again, within that elastic limit, all right? And then to relate the two, there was this constant K, and the constant K was the spring constant, okay? That's what it's called. All right, and I'm applying this to a spring, but understand that anything that is elastic, anything that can stretch, even if it doesn't look like a spring, will have some K associated with it. It'll have some spring constant associated with it, okay? And physically, you can think of the spring constant as just how stiff is this material, okay? So if this material is very easy to stretch or compress, then it has a very small K. And if it's very hard to stretch, then it's going to have a very big K. And you could see that because, you know, if you only want to stretch it a little, if delta L is, say, small, but K is really, really big, then F is going to be big, okay? And so that basically says if K is big, then you're going to need a big F for a small delta L, and that means something which is rather stiff, okay? All right. Now, how do we relate this, though, to properties of materials? Like you take some particular object, which is, you know, elastic. You could take the human, you know, a human bone or something like that. And you're going to say, well, how do I even apply this? Like, how would I find K for this human bone? Okay. It turns out that K, the spring constant, can actually be broken down into some geometrical properties and a property of the material itself. Okay. And that's my point here, okay? So K is first going to depend on the type of material, all right? Obviously, Jello is more elastic than something like steel, all right? So it's easier to compress and stretch Jello than it is to compress or stretch steel, all right? But that's not all. That's just the type of material. So that goes into determining what K is. It's also going to depend on the thickness of the material. Okay, in other words, its cross-sectional area, because you could imagine, you know, Jello or maybe steel. Steel is a little harder to picture because it's pretty rigid, but I think you'll understand this. If you have some like a really thin steel bar, okay, thin enough that you might call it just like a wire. Well, a wire is easier to stretch because it's less thick than a thick bar of steel. Okay, and the same is true, say, with an elastic for an elastic band. If you have a very thick elastic band, that's going to be harder to stretch than a thin elastic band, even if it's made of the same material, okay? So we could be talking the same material, but now a thicker material is going to be, a thicker object is going to be harder to stretch than a thinner one. And so that's one of those geometrical properties that goes into determining K, which is the cross-sectional area. But that's not it. There's also the length of the material, and this one's the harder one to see. But if you have a short material, which is stretchy, then you're going to have to apply more force to it to, say, to stretch it the same amount as a larger material, longer material, of the longer object of the same material. Okay, and you might go, why? And the reason is that when you have more length of the material, there's more length over which the stretch can be distributed. Okay, so if the material is short and you're trying to stretch it 1 centimeter, then there's a little bit of material that you're trying to stretch 1 centimeter. But if it's long and you're trying to stretch it 1 centimeter, well, then that's not that much, because that 1 centimeter stretch is going to be distributed over the entire length of the object. Okay, so that's a little bit subtle, but you know, those are the three things that go into determining what K is. Okay, and so here's the equation for it and a picture. You can picture this object here. Say it's a cylinder, all right, and the cylinder has some cross-sectional area like that, A. All right, and the cylinder also has some length before you stretch it, and we'll call that L naught. Okay, like that. Or actually, in this case, I said stretching, but actually compression. Okay, so you can either compress it or stretch it. So the original length of the material before you apply any force to it is L naught. Okay, and then we're going to apply some force F distributed over that cross-sectional area there like that, and that force F is going to compress the object. It's going to shrink the object's length by a distance delta L. Okay, so this picture is actually showing a compression, but it would be the same thing for a stretch. Okay, so let me go through those parameters once again. L naught is the original length of the material. A is the cross-sectional area. Cross-sectional area just means its thickness. Okay, so we have length L, cross-sectional area A. I'm going to apply a force F to this material, and it's going to compress a distance delta L. Okay, so that's how much the length contracts under this force that you're applying. Okay, now the force has to be balanced on top and bottom. Okay, so this is maybe a subtle point, but I think it's important. Obviously, if you just push on one side of the object, you're just going to move it. Okay, because Newton's second law. So to keep the object in place, not only are you going to push it on one side, but you got to push it on the other side like that, and then it'll compress. Okay, so the force F that goes into this equation here is going to be the same force on the top and the bottom. Okay, so you're applying the same force on the top and the bottom of the object. One, just you could think of it as keeping it in place, and the other one as compressing it. Okay, and so this formula here comes out of an analysis of this material. All right, and the formula itself is not derived from, or I guess it could be derived from deeper principles, but that would be a difficult derivation. You could just say, well, that's something that is experimentally verified in the lab. Okay, and what does it say? If you take the force F and you divide by A, that kind of gives you the distribution of the force over that cross-sectional area. Okay. Later on, when we get to fluids, we're going to see that this F over A turns out to be pressure. Okay, I'm getting a little bit ahead of myself, but that's okay. It's important to understand that the idea of a force may not be sufficient to really explain what's going on here. It's not just the force, but it's the force and how much area is it distributed over. Okay, and I'll talk more about that when we get to pressure. Okay, so that's F over A. And what's that going to equal? Well, that's going to equal the delta L over L, which is the ratio, the percentage shrink because of the compression. Okay, so if you take delta L, that's like how much it shrunk, and L naught was its original length. So say the original length was 100 centimeters and it shrunk by 1 centimeter. This would be 1 centimeter divided by 100 centimeters, or 1 in 100, which would be 0.01 or 1%. Okay, so you can think of this delta L over L as kind of like the percentage shrinkage. Okay, but expressed as a fraction, not as a percentage. And then there's another quantity here, and that's E there, like that. E is known as the elastic modulus, or sometimes called the Young's modulus. You'll hear me using both terms. Okay, Young because it was named after the physicist who discovered it, and it's basically only a property of the material. Okay, let's scroll down a bit here. So E is this elastic modulus, and it's purely a property of the material. So if you say to me steel, it has an elastic modulus associated with it, irrespective of the shape of the object. Okay, just the fact that it's steel is E. All right, and Jello has an elastic modulus. Bone has an elastic modulus. Anything which can stretch or compress in the form that I showed here will have associated with it an elastic modulus. All right, and so we're going to use this formula here in a bit to solve some problems. But before I do, let me show you what units are going into this equation. Okay, so remember from last semester, the force is measured in newtons, MKS. Okay, so I'm going to continue with MKS throughout the second semester as well. All right, A, the cross-sectional area. Well, if you're measuring out, like, I don't know how much carpeting you need for a room, you want to go to the store and say, well, they'll ask you how much carpeting do you need. You give them the length of the room and the width of the room, and if you multiply length times width, you get an area, so that's meters squared. Okay, so area is measured in meters squared. Now, on the left-hand side of that equation, let me just scroll back up here, this side right here, okay, you had force divided by area. All right, by the way, that's sometimes in this business called the stress. And the other side, the delta L over L, is called the strain. Okay, I don't use those terms that often, but you may see them in other contexts, so I just mentioned them in passing. Okay, back to the units. Notice that F and A come in that ratio like that, F divided by A. And so if you go down here and you say, well, what are the units of F divided by A? They're going to be newtons per meter squared. Okay, so those are the units. As I said, this turns out to be pressure. And we're going to be using this quite often when it comes to fluids. So I might as well introduce right now the unit for pressure in MKS. And the unit for pressure in MKS is pascals. Okay, Pascal like that, written PA. Okay, it looks a little funny because it has two letters to the unit, but you know, P and one of them is capital, PA like that. But that whole thing, PA by itself means 1 Pascal. And if you say, well, how big is a Pascal? You know, is it big? Is it small? It's kind of small. A Pascal is just 1 Newton distributed over a meter squared. So imagine a meter by a meter, a square, which is a meter by a meter. And imagine just 1 Newton of force. And you say, well, how big is a Newton? So remember mg. Okay, so if you had 1 kilogram, G is about 10, 1 kilogram weighs roughly 10 newtons. So only 100 grams would weigh roughly 1 Newton. Okay, so 1 kilogram is 10 newtons, so 100 grams, that would be 1 Newton. And 100 grams, you know, you can hold that in your hand. It's not a lot. It's not that much. Okay, so 100 grams like that. I think a pound, if your brain works in pounds, I think a pound is like 460 something grams. Okay, so like, you know, like 4.5 cylinder 100 gram cylinders would be a pound. So we're just talking about 100 grams. That 100 grams is a Newton, and imagine that distributed over a meter squared. It's not a lot. So a Pascal turns out to be quite small. In fact, we'll see later when we talk about atmospheric pressure that normal atmospheric pressure at sea level is 101 kilopascals. Okay, kilopascals, thousands of pascals, so it's 100,000 pascals. So I'm getting a bit ahead of myself, but that's the unit for F over A. Okay. Now, what about the other side of the equation? Well, the other side of the equation was delta L over L. Now, both of those are measured in meters. So if you have a meter divided by meter, it cancels out and it becomes dimensionless. So that's why that delta L over L, you could think of it as kind of like a fraction of how much the length changed, or a percentage. You know, again, in my example, 1 centimeter compression over 100 centimeters would be 0.01 or a 1% change. Okay, and you know, when you're talking like ratios like that, they're dimensionless. Okay, and so if you look at the equation, that means that elastic modulus has to also be in pascals. Okay, so you take a look here and you say, okay, this side here, the F over A, that's in pascals, newtons per meter. Okay, and this delta L over L, that has no units associated with it at all. So in order to balance the units on both sides, that E must be in newtons per meter squared pascals. Okay, so that's how the units of this work out. Okay, one more thing before I actually start doing problems with this. Actually, two more things. I got to show you the other types of deformations that can occur. But you take a look at equation 2 and you go, okay, well, you started off the lecture talking about this equation here, okay, and for a spring, and now I've got this equation here, okay. And how do the two relate to one another? Because, like, suppose I wanted to use this equation for a spring. Does it even apply? And there's hope, because there's an F in there, okay? And there's also a delta L. And you say, well, how does it work? Well, if you just rearrange this equation, I can make equation 2 look like equation number 1, okay? And so over here, if you take equation 2 and you just rewrite it as, you just isolate the F on one side and you isolate the delta L on the other side, and you just make the, I guess multiply both sides by A, divide both sides by, just multiply both sides by A, and then just move the L naught into this bracket here. You get E times A divided by delta L. That is your K. Okay, so you'll get F is equal to K times delta L there. So if you take a look at K, here written as EA divided by L naught, you could see what I was talking about earlier. K is going to be proportional to the cross-sectional area, meaning the bigger the cross-sectional area, the bigger K is. It's going to be inversely proportional to the length. You can see here that L naught is on the bottom. So the bigger the length, the smaller K is. And again, that's because you've got more length to stretch, and so the stretch, your delta L gets distributed over a longer length, okay, and it can sustain more stretch. And if it can sustain more stretch for the same amount of force, it means a smaller K, okay? So the bigger L naught is, the smaller K is. And then, of course, there's E, which is that elastic modulus, and that's purely dependent on the type of material, okay? So there you go. Those are the three things that go into determining K, and you can see how equation 2 can actually be rearranged to look like equation 1 and explain, you know, the physical properties behind K. Okay. So just two more things before, two more equations that I need to give you before we can do problems. So in the previous diagram, what I showed you here was what's known as a compression, okay? And what a compression means is exactly what it sounds like. You just grab the object on the top and the bottom and you apply force and the object will compress, okay? Conversely, I can take that object, grab it on the top and bottom, and stretch it, okay? Now, whether you're compressing or stretching, the same formula applies, okay? And so this is called a linear compression or linear stretch, okay? The word linear is because it's along a line. So if the object is here and I'm pulling this way, it's stretching like, you know, along this line here, all right? It might have deformations in other directions, but the force is just purely along a line, okay? So either like that or like that, okay? And so that's why it's called a linear compression, all right? But I could do something different. I can apply my forces like this, okay? And so imagine here, this is a block. So just focus first on the thick block here like that, okay? And this block has a cross-sectional area A. Right? I can't show you that because it's a three-dimensional block is obviously three-dimensional. But just remember, just imagine that the base of the block has a cross-sectional area A. So here you might see the length, but you can't see the depth of it because that's like into the page or into the screen here. Okay, and it has a height L naught. So it has a thickness A and it has a height L naught. But I'm not going to squish it. What I'm going to do is I'm going to grab the top and bottom like this, and I'm going to shear it. Let me see if I can do this like this. Shear it like that. So I'm going to apply the forces perpendicular to the length. Okay, so previously I was squishing it like this. Now I'm going to do this. Okay, so that's known as a shear. Okay, now this is important, especially, you know, when you go past that elastic limit with bones, because that's going to be really bad. Okay, so, you know, if you have a bone and, you know, you apply a force one way in a bone and a force another way in a bone, like my forearm here, I put a force this way and a force that way, I'm going to shear the bone. It's going to be one of these situations. Okay, again, that's beyond the elastic limit, so that's not our concern, but, you know, that's sometimes we talk about shearing things. That's what we mean. Also, this is how scissors works, which is why we sometimes call you know, scissors shears. What's happening there is you take a look at the blades of a scissor. You know, one blade is coming down this way, another blade is going up that way, like that, with the page in the middle or the paper in the middle. And what you're doing is you're forcing one side of the paper up, another side of the paper down, and that'll shear it. Okay, again, that'll be past the elastic limit. Now, what does the formula for that look like? Exactly the same as the previous one, but now instead of it being the elastic modulus, it's what's known as the shear modulus, okay? So the same material might have an elastic modulus if you're deforming it by stretching it or compressing it, but it might have a different modulus if you're shearing it, okay? So same formula, it's just going to be a different number here. Now, in the problems I'm going to give you, I'll be quite honest, these are pretty easy problems, okay? The only difficulty students might have is one, identifying whether you're talking about a shear or compression, or the next one, which is the bulk modulus, okay? Identifying that, which is still pretty easy to do, but it's the units, because these have some, you know, pretty big and small units. So we'll look at that in a minute. But other than that, you know, there's not a lot here. You know, it's the same formula. It's just identify, was it a stretch, a linear stretch or linear compression? Then use the elastic modulus. Is it a shear? Well, if it's a shear, then use the shear modulus, okay? And that brings us to the last type of compression that we're going to do, and it is known as a bulk compression. And this is when you apply the force uniformly over the entire surface, okay? So you can imagine here some object like this, and you're going to apply this force. You can see my arrows here like that. It's going to be applied uniformly over the entire object. Well, what's going to happen is the entire object is going to shrink, Okay, so this is known as a bulk compression, and I guess the opposite of that, although I didn't show it, would be a bulk expansion. But a bulk compression occurs when you apply a force uniformly over all its surface and the whole thing shrinks, okay, in volume. All right, so the formula here is a little bit different than the previous ones. Okay, you still have an area, but now it's not just the cross-sectional area, it's the entire surface area of the object. Okay, so if you've got a sphere, it's going to be that surface area of the sphere. Okay, or if you've got a block, it'll be the surface area of the box. So that the block makes up the surfaces of the block. Okay, so it's that, and then when it shrinks, it's going to shrink in volume. So if you see the formula here, you're going to have that it's going to be delta V, not delta L, but delta V, that's the change in volume, okay, divided by V naught, which is its original volume. All right, and that's going to equal to F, which is the force that you're applying. But now this force is applied over the area A. It's not the cross-sectional area, it's the surface area of the object. Okay, so again, the formula looks very similar, but now there's a couple of changes. The first change is B is this bulk modulus. Okay, so the same material, say steel, can have an elastic modulus, it can have a shear modulus, and it can have a bulk modulus, and all three of those numbers are different, or can be different. Okay, they can be different. All right, and so it's going to be F over A is going to equal the bulk modulus multiplied by delta V over V, so V naught. Okay, and again, V naught is the original length. All right. The units here, I'm not going to be doing a dimensional analysis for all the formulas. They're the same, okay? So because that delta V over V naught is dimensionless, all of these, whether it's the elastic modulus, the shear modulus, or the bulk modulus, are going to have the units of F over 8, which are pascals, okay? Which is pascals, okay? So they all have the same units, pascals. All right, so that's it. There's no more to the theory, and so let's just do a problem. All right, so what do I have here? I say I have a bar of aluminum, which is 1 meter long. Okay, so you can imagine a bar of aluminum 1 meter long, and it has a cross-sectional area of 1 centimeter squared. This is the one that gives a little bit of problems. Okay, so because centimeter squared is not in MKS, which would be meter squared, so I have to show you how to convert that one. Okay, and how much force is required to stretch it 1 millimeter? Okay. And I give you three numbers. Obviously, I'm not going to have you guys memorize elastic and bulk moduli and shear moduli. Okay, on a test I would give you them. And if I had, or on an assignment, and if I had like several materials, just to see if you're thinking about it. I'd say these are the elastic, shear, and bulk modulus for steel. Here they are for aluminum. Here they are for bronze, something like that. And then you have to choose the right one. Okay. Again, it's pretty simple because you just choose the correct kind of deformation, and so like in this case, it's a stretch. All right, and I say stretch, so it's a linear stretch, and so you go, aha, I have to use the elastic modulus. And if you have different materials, you would say, well, which one do I want? Well, that one's easy. It's just, for the one for aluminum. Okay, so this is the number we want to use for the elastic modulus. It's 70 gigapascals. And then you take a look at the giga and you go, what's that? Well, because these numbers are both very, very big and very, very small, that I think is the only real difficulty you might have with using these equations. Otherwise, it's just plugging in numbers. Because you're going to have different units, you got to put them all into MKS, okay? And you got to know some of those MKS metric prefixes to be able to convert to MKS. The units for force over area are pascals, but this is gigapascals, okay? And giga is billion, 10 to the 9, all right? And that's because, as you can imagine, aluminum is pretty strong. It's not easy to stretch, okay? And so the elastic, all the moduli are going to be in the gigapascal ranges. Remember, Pascal is pretty small, okay? Atmospheric pressure is already at 100 kilopascals. All right, and that kilo is 1,000. So here we're into the billions of pascals. Okay, so let's go ahead and start to solve it. So we have this formula here, okay? And what am I asking you to solve? I'm saying how much force is required. So before I even start plugging into it, I just rearrange it and isolate the force, which is what I want to solve for. Another variation of this, I could say, I could tell you how much force I'm applying, and I could ask you to calculate you know, the how much it will deform. So then you would just isolate your delta L on one side and then plug in. Okay, so you have the elastic modulus multiplied by delta L over L naught multiplied by A. Okay, and let's look at the quantities one at a time. So let's start off with L naught. L naught is 1 meter. It's already an MKS. Great, no problem. Okay, delta L, I tell you, I want to stretch it 1 millimeter. Okay, so 1 millimeter. So you go, well, how big is a millimeter in meters? A millimeter is 1,000th of a meter. Okay, so you need to know these metric prefixes. You could just Google for them. You know, but you know, you should memorize at least the ones that we're going to use in class. Okay, so you should know what a millimeter is. So 1 millimeter is 0.001 meters, or written in scientific notation, it's 10 to the minus 3 meters. Okay, so great. There's your delta L in MKS units, 10 to the minus 3 meters. All right, that was pretty easy. It's whenever you get like centimeters squared or centimeters cubed, which you'll see later, then it gets a little bit trickier, because that square there means that you've got to convert the centimeters to meters twice. Okay, so that's why I'm not going to do this every time, but just to show you what's going on here. Think of that 1 centimeter squared as 1 centimeter times centimeter. So I want to convert the first centimeter to meters. And so I multiply by my conversion fraction here, which is 0.01 meters divided by 1 centimeter. Okay, that'll convert one of the centimeters, but I've got to do it a second time for the second centimeter. Okay, so the typical mistake that's made here in converting is you'll see the centimeters and you go, well, I'll just convert it to meters, and you just multiply by it by once. But no, you have to do it twice. You have to multiply by the conversion factor twice, because it's centimeters twice, or centimeters squared. Okay, so you got 0.01 meters divided by 1 centimeter, and then again 0.01 meters divided by 1 centimeter, and that works out to 10 to the minus 4 centimeters squared. So 1 centimeter squared is 10 to the minus 4 meters squared. Okay, so again, a little bit subtle, and it's because you have to convert each one of those centimeters. Okay, and now we get down to the elastic modulus. We decided that we wanted E, because this is a stretch. Okay, and it's 70 gigapascals, and giga is 10 to the 9. Okay, and so I wrote a few here. So these are the ones that are bigger. We did the smaller ones last semester, like we saw centimeters quite a few times, and we saw millimeters. Okay, and in this course, second semester, we're going to go to much bigger things. And so we're going to have to look at not only mega, but also giga. And we're also going to go to much smaller things. So we're going to have to look at micrometers and nanometers, but that's later in the course. For now, you know, when it comes to the elastic modulus, they tend to get big. And so you might see like kilopascals, and kilo, just remember that's 10 to the 3. Okay, from the Greek for 1,000, so 10 to the 3. Mega, M, that's a million. A million is a 1 followed by 6 zeros, so it's 10 to the 6. A giga is a billion, and that's 10 to the 9. Okay, so here we have 70 gigapascals, so take out the giga and put in 10 to the 9. 70 times 10 to the 9 pascals. Okay, so that's what we're going to use right here for E. All right, well, now that we've converted all those things to MKS units, now plug into the equation. And I didn't even bother writing the units here, because they're all MKS units, so you know the answer is going to come out in MKS. So for E, here, let me just scroll up a little bit here. I don't think I could. Yeah, there we go. For E here, we're going to put in 70 times 10 to the 9. For delta L, we're going to put in 10 to the minus 3. For L naught, we're going to put in 1. For A, we're going to put in 10 to the minus 4. Okay, which we got right here. All right. Now, just multiply that all out on your calculator. All right. And pretty easy to do, but be careful. Like, you know, it's good to work in scientific notation, because otherwise, if you try to, you know, put in all the zeros there manually, some calculators you can't even do it. You have to use that like EE button or whatever. Make sure you understand how to do that on your calculator. I can't tell you how to do it in general, because every calculator is slightly different. Okay, so you know, just figure out how you do like 70 times 10 to the 9, like how to do scientific notation in your calculator. Multiply this all out, and you get 70 times 10 to the 2. Okay, and that's 7,000 newtons, or 7 kilonewtons, and that would be the answer. Okay, so over here, in answer to the question, we have a 1 meter long bar. We're going to stretch it only 1 millimeter. It has a cross-sectional area of 1 centimeter squared. How much force does it take? Okay, and it turns out to take 7,000 newtons, which is a lot, but it's not an extraordinary amount. And you could certainly do this either in a lab or like even like in some machine shop or something like that. You could easily using some kind of like a vise apply 7,000 newtons of force. Okay, and then this thing would actually shrink, or sorry, in this case we're stretching it. It would actually stretch by 1 millimeter. Okay, last thing, maybe I'll say just a little bit more how to work with scientific notation here, like that. I personally like to do it just manually. And what do I mean by that? Well, what I'll do is I'll just look across here, and never mind the 10 to the whatever exponents. Just like ignore that 10 to the 9, ignore the 10 to the 3, and ignore the 10 to the minus 4 there. It's just going to be like 70, and there's no number there, so like 1 and then 1, so I get a 70 out front there, like that. Okay, so I just look at the numbers without the exponential parts, like the 10 to the whatever. Okay, and then I look at the exponentials, and when you multiply exponentials, the exponents add. So I'll go here 9 minus 3, okay, which is 6, and then minus 4, all right, and that's 10 to the 2. Okay, so I'll just do the exponents manually. Now, if you're multiplying them, of course, you add the exponents, but if you're dividing, then you subtract the exponents. I'm sure you guys have seen that before, but I just don't want you to make a mistake on an assignment or a test over some exponential, okay, because you might do it wrong on your calculator. Okay, so that's it for elasticity. Not too much to this topic, but it is important because I don't know what you guys will do later in life, but if you're dealing with materials, and I'm thinking of like the human body, yeah, the human body, we apply forces to the various segments of the human body, and yeah, things will compress and expand, and as long as you're within that elastic limit, these are the equations that work. Okay, even when you're like go diving, underwater, there's pressure on you. We'll talk a little bit more about that later. But you know what? Your body's going to get actually squished in, and it's going to compress a little bit. It's going to have a bulk compression, okay? Or maybe another example would be, I don't know if you've ever tried to do this. It's kind of hard to do. Take a air balloon and then bring it underwater. You'll actually see that, like, if you were crazy like I was when I was a kid, taking it underwater, it'll actually shrink as you go underwater because the pressure will compress the air inside it, and you'll have a bulk compression. Okay, thank you very much for listening. That's the end of our second lecture.